Gonna do another video for you today. In this one I am gonna show you a routine that I wrote that will help me set up and do Frac-out calculations or inadvertent return calculations. This is a previous example that I set up. This is the plan view of a drawing where we have a drill going underneath a two-lane interstate. Here is the entrance and here is the exit over here, and we have our different vertical points of curvature and VPTs for our vertical curves marked in the plan view. I'm going to give you a quick shot of the profile before we move forward. So here's a layout that I had done previously. This has got the profile cut across the two lane. It's actually two lanes in each direction, and just a very arbitrary generic design. Okay, so the first thing you would do is you would plan your soil borings. So I'm going to go back to the plan view, and wherever those are taken, you can mark the same way I mark these entrance and exit points. So I'm going to use a Civil 3D object, and the good thing about the Civil 3D object is that when you mark something in the plan view, it will project it to the profile view, and I'll show you how that works. So I'm going to use a Civil 3D structure that I've set up a special style for. Let's say we have one boring here and we have another boring here on either side of the road. Okay, I'm going to pull this off. I've got a pre-set up style for labeling. It tells you some very good information. So I'm going to go in here and I'll call this B1 for boring 1. Okay. Check something real quick. Okay, and I do need to set an elevation. And if you have your surveyor go back out and pick up the boring elevations after they have done the geotech investigation company has done the borings, you actually can set the elevation here for where that boring was taken. So this one, in case, so this is elevation about 25, so I'll just set it there. Let's say structure properties. Elevation 25. And then I'll set this up as B2. Okay. So this is pretty good information because it actually, it being a structure, it tells you the station along the alignment and the northern and eastern and even the offset. And normally you don't want your borings taken right on your horizontal directional drill alignment. You don't want to create pathways for inadvertent returns to come out on their own. So watch. So now I'm going to go to the profile. And I'm going to come into the profile view, and I'm going to tell it that, actually I did the style. Let's do the view. I'm going to tell it that B1 and B2 I want to add to this profile. And then they get added right here and here. See, so I'm actually going to add a label to both of these. Okay, so now that we have our borings projected to our profile, we can bring in the actual boring logs as images. I've set them off to the side, brought the actual boring logs in for the two borings, and I can actually put those right on top of the points that have been projected into my profile. So from here I could either print this out, could give it to a geotech who could help delineate soil strata, or if you have a geotech that's a little bit savvy, he can actually create layers himself right here in the AutoCAD environment. Now I'm going to just arbitrarily imagine that these soil layers have been delineated into something that makes sense So let's go with this. 4 soil layers. I'm now gonna freeze the soil layer, the boring logs. Okay. So now that we've had our soil layers delineated, I can bring in the soil IR information block, and that's what this is right here. This is kind of the interface, dashboard, whatever you want to call it, for doing the different design. So I'll show you how all this works. First thing you have to do is we have 4 soil layers. So I'm going to come up into my tools. I'm going to create 4 layers in my box. Okay, so those are over here. And I can even then, just for labeling purposes, let's label those. Okay, so we got layer 1 here. Layer 2 here. Layer 3 here. And then the trick is to, whatever the top of that soil layer is, I need to make the same layer as these numbers. So I'm going to do a couple of little quick things here, real quick. I have to turn both of these lines into polylines. Polylines is the only thing that the program recognizes. Done that for the profile. That's a polyline now, and now I'm going to do this for the bore. Okay, so now I've done that. Now you need to make the top of each layer. So the top of layer 1 will be this. Will actually be your topo line. The top of layer 2 will be here up until this point. Break this line in 2 here. Both of these will be layer 3, and then the top of this line will be layer 4. I then need to put this on the layer for the The last thing you need to create is the water table. Normally you would get this from your soil borings. Let's go look at this. Let's imagine that there's actually some water in both of these channels on either side. Then I'm going to put this on the water surface layer. I'm going to put this on either side. on the water table there. I'm now ready to do my Frac-out calculations, except I need to define my soil parameters. Okay. To do that, I have a edit soil layer dialog box. I'm going to call this layer 1, and let's just call it a sand, or let's say SC. And just quick and dirty, I've got some default values, but it would be nice to have these actually generated from a qualified geotechnical engineer. Those two. You can have a play if you wanted to. Just for some variety, I'm going to give these a little bit different values. So once you get the values in there, there's actually some tools that I have based on some references where you can further define these a little bit more exact. So this pulls in the values that was in the listing for the soil layer, and then say here, based on this Ting-Meyerhoff reference, you can estimate some of this stuff based on in count. So, you know, let's just say we had 20 blows per foot. You could hit calc and it'll actually estimate some other types of values for that maybe you want to modify a little bit. This will give you a relative density, which down here based on NavDocs you could say, okay, based on SM 50% relative density calc. So there's tools actually built into this to help you come up with some of the soil parameters. And then once you find what you like, you know, whether it be the 33, the 27, you can key it in here. So I just wanted to give you that as an example. Got a similar one for the underneath shear strength over here. You can hit this, and then based on different references, Roth or Terzaghi, you can actually come up with a different SU. Now the SU actually doesn't go into the calculation for the Delft equation, but there's other methodologies for calculating inadvertent returns where the S sub U does become important. But I just wanted to kind of show you, some of these tools that is built within this. Okay. All right. One of the things you have to do is align the grid. This sort of tells the program where your profile is spatially, so that it can reference some of the data. So you just sort of pick a reference point. You tell it that this just happens to be station 0, elevation 0. Horizontal scale for this is 40, vertical scale is 4, and then it wants to pick the beginning of your line of work for your profile. So we'll just pick that there. Select the drill path parameters block, and that will populate the information here. So now the program, using this block as a reference, knows where in space this profile is. And then the last thing you kind of want to set, so as it does its calculations, is the stuff for the drill head pressure. So this is stuff based on sort of a standard method using Bing and Plastic methodology for calculating drill head pressure. So you put in here your drill weight. I usually use 50% for my RP max. The bore head radius, that's pretty good. These numbers might be a little high here. And then you estimate a flow rate for your drill mud. Let's just go with 150. It's kind of small. And then there's your drill pipe. So let's go with 5 inches. So let's change that to, actually let's go with 4 inches. So that'll be there. Left to right, you can actually run this program in either direction. We're going to act like we're drilling from the left, where the entrance point is, to the right. Here you set your calculation interval. You can set this to anything you want. The smaller you use, the more intervals it's going to do, which is going to take the program longer. Normally, just to kind of get an idea of where I'm at, I'll start this out pretty high, and then for the final plot, once I get the design exactly where I want it, I'll drop it back to something smaller to get a better graph. So right now I'm not going to tell it to graph it, and I'll tell you why in just a second. So now I can literally run my program. Okay, so now I can run my my R calculations. So it does it in the background. Now it's finished. I'm going to turn on the text screen so you can kind of see what went on in the background here. So here essentially it goes through an interval. So let's say for iteration number 5, it cut a profile, and here's all the elevations it got from the graphics. And then based on that, it did a calculation. And essentially I run this the first time. I'll tell you what we're going to do here, just so we can look at these numbers a little bit more later. I'm going to actually highlight them, and we'll copy and paste them into a text document so we can analyze it a little bit more later on. Let me just do that. Like so. Okay, so the purpose of running this the first time without it doing any outputs on the plots, it actually calculates basically the max pressures that's going to be seen from both the drill head and from the overburden pressure. It uses the Delft equation. The program actually has the ability to use other methodologies, but the Delft is what people are most familiar with. So that's what I'm using for this video. You can see here locally and in respect to surface returns, what this is just sort of locally is the straight application of the Delft equation, and then for multi-layered soil strata it does a weighted average, and this is the weighted average. So you can see out of these three, 16 psi is the drill head pressure, 60 to 65 psi. So if we set up our graph to plot up to, let's say, 70 psi, we would be able to encompass all the pressures that are seen from this example in this profile. So I'm going to insert what's called a minimum marker. I'll set that right here, and the bottom range is going to be a psi of 0, and then I'm going to set a max marker. And we'll set this up at the top. So it comes in at 1,000, but I can change that. We're going to set it to 80 psi. Let's go with 80 psi. So essentially it's creating a secondary scale over here on the right, where the bottom of the scale is 0 psi, but the top of the scale is 80 psi. So now I can come back into my drill parameters, and I can say, hey, I want to now plot the findings to a graph. Now when I run the IR calculation, I'm going to pick all the objects. And there it's done. change the LT scale. See if I can get some better spacing on these lines. There we go. So one of these lines is one version of the Delft. The other line is the other version of the Delft. The yellow line is the drill pressure. And there's your calculations. As long as the drill pressure is below the overburden pressure, then you have a good calculation. So now, do you see these lines here that say 6, 11, and 16? What that is your iterations. So starting here, here I'll tell you what. Let's change our interval to a smaller interval. So I'm going to erase the calc that it just did. I'm going to come in here and edit. So now instead of doing a interval every 30 feet, let's do one every 10 feet. Give us a little bit smoother graph. Take a little bit longer to do. So perform my arc out. Pick all the objects again. So now you'll actually have more intervals. So it looks like this drill may be about maybe 600 feet long, maybe 500 feet long, so you should have about 50 intervals. So there you go. So there's your calc, and so you really don't have to worry, at least from this example now, warranted, you know, I didn't put in actual geotechnical soil parameters. You know, we would spend more time on that exercise if we were doing this for real. But I just sort of wanted to show you the example. Now let's go back to what we got out in the text. In my program, I can actually set it up to export this for every interval into a text file that can actually be submitted with the report, so that whoever wants to follow along, essentially a reviewer could take any interval they wanted to. In this case, what was interval 6 on the previous 30-foot iteration length, and they can put these elevations in, and they can calculate a pore water pressure. You know, here's the water table. They can basically mimic everything that is in the Delft equation and sort of reproduce the calculations for themselves. And down here, it tells you the factor safety. So that's essentially based on, at this particular location, the drill head pressure was 12.88. The Delft pressure for local losses was 44.98. And if you did the math, you get a factor safety in this location of 3.5. So just total transparency. So hope that you enjoyed this. So this is just one of the programs I've written to do HDD calculations that I don't really think anybody else in the industry has anything like it. You know, of course, if we made changes to our design, if we wanted to modify the soil parameters, if we wanted to change our drill head inputs, you know, we could make those modifications very quickly right here in the AutoCAD environment. So thank you for watching, and we'll catch you next time.